Okay, everyone. Today I'm gonna talk about a theme of how to encode entanglement into a wave function or into a state. So in the past lecture, I talked about a mathematical criteria. Okay, mathematical way of telling whether some state is entangled or not. And the mathematical technique is known as the singular value decomposition or the Schmidt decomposition. Uh, these names are used interchangeably in the literature. And when you break down some many-body wave function into the Schmidt's form, and then you find that this breakdown between the wave function for the left-hand side and the wave function for the right-hand side involves the superposition of more than one of these f's, then the more than one f alpha is non-zero. Then I would say that the state is entangled. And otherwise, if only one f alpha is non-zero, then it's pretty obvious that we have just succeeded in transforming a many-body state into a product of a state that reside on the left side of the system, and another state that resides on the right side of the system. So, by definition, this is a unentangled or a product state. Okay, so that was the mathematical way of telling whether a given wave function is entangled or not. But today we are gonna talk about a different question and how to answer such a question, which is how to start from a product state. That is a state with no entanglement, and then somehow evolve that into an entangled state. Okay, first of all, I have to clarify exactly what I mean by evolving a state. And of course, secondly, I have to tell you exactly what is the recipe for turning a product state into an entangled state. So those are the two things I will try to accomplish in this lecture. Okay, so think about the solution of the Schrödinger equation, which has a solution that formally looks like that. And actually, this Hermitian operator raised to an exponential form is a unitary operator. Okay, so the evolution of a quantum state occurs by means of multiplying or acting with some kind of unitary operator on a given quantum state. All right. So we're gonna apply this idea and then try to apply some sort of unitary operation on a product state. To see whether through this unitary operation, the product state can evolve into a non-product state that is an entangled state. Okay, so let's get down to a more practical implementation or explanation of the idea. So I give you this example of a product state. So here each psi represents the state of a single qubit, etc. Let's say we have an n qubit system, which I draw schematically like this. So this is a qubit 1, this is a qubit 2, qubit 3, 4, etc., going all the way up to the qubit n. And each qubit is described by some sort of wave function, psi 1, psi 2, psi 3, and psi n. Okay, but the overall wave function is simply a product of the individual wave functions, which define the state on each qubit. So this is a product state. Now, as in this general scheme of evolving a given quantum state, let me try to evolve each one of these qubits according to some unitary operation. So now what I mean by that is I will transform this initial qubit wave function into a different wave function which is achieved by acting with some sort of unitary operator on the initial state. And that I'm going to call psi 1 prime. And I'm going to do the same thing for each one of these qubits. Okay, so now keep in mind that I don't have to apply the same unitary transformation to all the qubits. I can choose to apply quite distinct unitary operations on each qubit. And then let's ask how this overall wave function would evolve after such an evolution. Okay, so the answer is pretty simple. Okay, now all I have to do is to change each of the psi I into a psi I prime. So psi 1 goes into psi 1 prime, etc. Okay, so this will be the shape of the new wave function after evolving each qubit according to a certain arbitrary unitary transformation acting on each qubit. However, from this form, it's clear that even after this evolution, this is still a product state. And therefore, there's no entanglement built in. Okay, entanglement is still absent. Okay, so clearly from this simple exercise, we can see that this is simply not a very good way of embedding entanglement into the given system. So now in order to create or in order to endow entanglement, we probably have to use some sort of a 2-qubit operation. 2-qubit operation acting simultaneously on this 2-qubit state. Okay, and because this unitary operation now acts simultaneously on both the qubit 1 and the qubit 2, there's a possibility that the resulting 2-qubit state, which I will denote as a psi 1 to prime, is no longer factorizable. It can no longer be expressed as a direct product of the individual qubits. And therefore, the result after performing the 2-qubit unitary operation is a wave function that has been entangled. Okay, that's the possibility. And now let me try to prove that the possibility is real. Okay, so how do I do that? Well, actually, I prefer to show that's possible by an explicit construction. Show by explicit construction. And of course, this is a way that physicists like to advance their way of thinking. They like to think by examples, and the more interesting the example is, the more insight they gain by playing with such an example. So I'm going to play with an example which turns out to be pretty interesting. So let me start with this product state. So this is a simpler notation for the product state of the first qubit and second qubit. So 0 means that the first qubit is in a state of 0. The second qubit is also in the state of 0. Now, on the other hand, write down some sort of an entangled state, which is 0, 0 plus 1, 1. Okay, so again, 0, 0 means that the first qubit is in a state of 0, and 1, 1 means that both the first qubit and the second qubit are in a state of 1. Okay, so I can easily convince myself and convince you that this indeed represents an entangled state. And the proof comes from doing the following thought experiment, which is, of course, the thought experiment that was initially proposed by Einstein, Podolsky, and Rosen in their famous epoch-making paper called the EPR paper, published in 1935. Okay, so EPR, published in 1935, is the first paper that indicated this interesting but very counterintuitive possibility in quantum mechanics, a possibility that can only exist in quantum mechanics. And the possibility was the following. So now, let's say you do a measurement on the first qubit. And then you happen to find that the first qubit was in a state of 0. Well, then, after performing any kind of measurements on the quantum state, the wave function undergoes what's known as the wave function collapse, which means that the very fact that you have discovered the first qubit to be in this state of 0 means that the initial wave function has now collapsed into this wave function, therefore effectively disregarding this other piece of the wave function as if it was non-existent from the very beginning. So now, because of wave function collapse, the second qubit state has no choice but to be exactly in the state of 0. Because the other possibility of the second qubit being in the state of 1 was eliminated along with the collapse of these other piece of the wave function into nothingness. Okay, but suppose that your measurement happened to give out. Let me just rewrite this wave function. Let's say your measurement happened to yield the other result, that your measurement on the first qubit gave a 1 as the state of the first qubit. Then, due to the postulate of the wave function collapse after the measurement, this part of the overall wave function is now completely gone. So therefore, the wave function of the second qubit, although we still have yet to make any kind of measurement on the second qubit as well, actually automatically goes into this well-defined quantum state with the quantum number 1. Okay, so a wave function of this kind has this interesting property that what you will measure for the second qubit depends entirely on what you end up discovering from the measurement of the first qubit. And that is the essential feature of the entangled state. Okay, so without having to go through any singular value decomposition analysis, just by virtue of this sort of thought experiment, we can already see that this is in fact representing an entangled state. Okay, so now we want to see if this unentangled state, which is a product state, can somehow be evolved into an entangled state like that. Okay, through some sort of unitary operation which acts on the 0, 0 state. Okay, so first of all, I'm gonna turn this problem into some sort of a linear algebra problem. Okay, and now because there are 4 basis states in this, these 4 basis states are 0, 0, 0, 1, 1, 0, and 1, 1. And I'm going to represent this 0, 0 state as a 4-dimensional column vector like this. And 0, 1 as another 4-dimensional column vector which is orthogonal to the first one. And there's in this third state with another unit vector which is orthogonal to the previous 2. And the final state as yet another unit vector which is orthogonal to the previous 3. Okay, so under this representation of the quantum state using the linear algebra, the unitary matrix, the unitary operation that we're looking for, will now have a 4x4 matrix representation. Okay, so the question is, what exactly does this matrix representation look like that will transform my 0, 0 state into such an entangled state? So I'm going to write down the answer and then verify that that is indeed the answer. So U12, which is a 4x4 unitary matrix, takes on the form like this. Okay. So what happens is that along this diagonal, you have a bunch of ones. And along these other diagonal, you have the ones for the half of the entries and the minus ones for the other half of the entries. All right. And this is actually not hard to show that this unitary matrix, this matrix is in fact unitary. So how do I express this? So with this matrix, you can verify that the U12 dagger is U12 inverse, and U12 dagger, which is complex conjugation followed by a transpose. Let me see. Yeah, you can easily work that out. In fact, thus the unitarity of this matrix can be proven by simply performing the necessary multiplication of the U12 with its Hermitian conjugate and showing that that indeed multiply out to a unit matrix. So I'm not gonna dwell on the proof because this is a simple exercise that you can do at home. So with this matrix, now what I can show is that if I multiply this column vector 1 0 0 0, too many zeros. Okay, 1 0 0, and I mentioned that this 1 0 0 0 vector correspond to the quantum state with both of the qubits being in the state of 0. The result of performing such a multiplication is, as you can easily check, is 1 0 1 0 0 1. Okay, which is, in terms of the quantum state language, is superposition of the 0 0 state and the 1 1 state. Okay. Okay, so we did find a unitary matrix which does indeed take us from the product state 0 0 to an entangled state like this. Okay. So now I want to explore the mathematical structure of this unitary matrix. And to that end, I need to introduce you to the something called the tensor product. And tensor product is a simple idea, although the name sounds pretty fancy. It's a pretty simple idea after all. So I'm going to go straight into an example of a tensor product, because explaining by an example is, I believe, the best way of getting rid of the fear for introducing a new language in mathematics. So I'm gonna think about the tensor product of the two Pauli matrices. Okay, as you know that each Pauli matrix looks like that. But for simplicity, I'm gonna write the second Pauli matrix as a simply sigma x. And now what happens when you do this tensor product is that this element 1 becomes the Pauli matrix, which we borrow from this second entry, and this also becomes the Pauli matrix sigma x, and this also becomes naturally becomes a 2 by 2 matrix of zeros. Okay, so this really means a 2 by 2 matrix of zeros. It's not a simple zero scalar, but rather a 2 by 2 matrix of zeros. Okay, so in this way, you can see that the doing the tensor product of two 2 by 2 matrices will give you a new matrix, which is 4 by 4. Okay. So that's the general scheme for basically that's a scheme for basically taking a product of matrices rather than taking a product of numbers. Okay, so when you take a product of numbers, the scheme is already pretty well known. It's something you pick up from memorizing the multiplication table. But when you do a product of matrices, in fact, the rules can be more complicated. And furthermore, there can be more than one rule of multiplying the two matrices. The most familiar example of a matrix multiplication rule is, of course, the one you learned from linear algebra. When you have matrix 1 and matrix 2, you multiply those two matrices by multiplying the columns of one matrix with the rows of the other matrix, etc. That's one way of performing or defining a matrix multiplication. And this tensor product is another way of defining the multiplication between the two matrices. And after doing these matrix multiplication through the tensor product way, the result is a matrix which is bigger than the two matrices that you use to perform the tensor product. Okay, so that's the difference. Okay, so the result of doing the tensor product of sigma x with another sigma x is 0, sigma x, sigma x, sigma x. But now let's honestly put down all the numbers. So sigma x is 1 like that. And here's another sigma x, so like that. Okay, so that's the tensor product of a sigma x with a sigma x. And here's another rule. When you act with this tensor product of operators on a product state, psi 1, psi 2, the rule is to have the first matrix act on the first state and the second matrix act on the second state, which results in the sigma x acting on the psi 1 for the first qubit and the sigma x acting on the psi 2 for the second qubit being joined together in a product state fashion like that. Okay. So now you can generalize this idea to an n tensor product of 2 by 2 unitaries. Sometimes people are lazy and they just call unitaries in place of unitary matrices. Okay, so the overall unitary matrix, which is how many dimensional? It's actually 2n by 2n dimensional matrix, because the Hilbert space for the n qubit system is in fact 2 to the n. So the unitary matrix acting on such a Hilbert space has to be 2n by 2n dimensional. However, you can break down that as a direct product or the tensor product of the unitary matrix is acting individually on each qubit. So now each unitary here is a simple 2 by 2 unitary matrix. Okay, so now the rule is that if a given unitary matrix can be broken down as a tensor product of the unitary matrices that act only on one qubit at a time, then the result of acting with this unitary matrix on the product state, psi 1, psi 2, product all the way up to psi n, is in fact just u1 psi 1 product u2 psi 2 product etc. all the way up to un psi n, which continues to remain as a product state. Okay, so this sort of factorization of a unitary matrix, let me call that a factorization or factorizability of a big unitary matrix into a whole bunch of 2 by 2 unitary matrices that are multiplied together through the tensor product. That's not a way to create entanglement out of a product state. So in order for the entanglement to arise, this sort of decomposition cannot happen. Okay, so the inability to break down the unitary matrix in this factorized form is equivalent to building in entanglement by acting with a unitary operator on the initial state, which is a product state. Okay, so I hope you realize that there is a clear connection, one-to-one connection between the physical language of building entanglement into a given wave function and the impossibility of a big unitary matrix to factorize into n different smaller unitary matrices. Okay, enough for the words. So this previous 4x4 unitary matrix I introduced, which is often called a Bell matrix, and because Bell plays such an important role in the science of quantum information, maybe we should stick with the language at this early stage. So this is a Bell matrix, Bell unitary matrix. And the state I wrote down earlier, which is this is called the Bell state. So Bell is the name of a guy who proved an important theorem in the quantum information science. And although I will not go into the detail of what Bell's achievement was, it's probably necessary and useful to introduce his name to the students at this early stage. So this Bell matrix, after you do the necessary homework, can be shown to break down into the tensor product of two unit 2 by 2 matrices. And and this thing. And I'm pretty sure I'm missing the overall factor of 1 over root 2. So let me put that in. Well, actually, the proof is quite straightforward. You can almost do it with your eyes. So minus I sigma y is 1 and minus 1 over here. And sigma x is 1 and 1 here. So if you take the tensor product of this, then this is just a big 4 by 4 unit matrix. And then if you do a tensor product of this and that, then you're going to have minus 1 here, and then one here, and then 0, 0. Okay, and indeed, after multiplying with this normalization, putting these two matrices together will bring you back to the Bell matrix. Okay, so that shows that this is the correct decomposition of the Bell matrix into a tensor product of smaller matrices. But the important thing is that Bell matrix is not a simple tensor product of two submatrices. It's a sum of the two different tensor product of the submatrices. And no matter how much you try to be clever, there's no way to simplify this decomposition any further into a tensor product of some 2 by 2 matrices like that. This just cannot happen. And so the impossibility of bring this unitary matrix into a factorized form like this, but instead the best one can do is to express it as a sum of the two different tensor product. That's an indication that this Bell matrix is doing something non-trivial to the wave function. And the non-trivial feature is, of course, that it's encoding some entanglement into the wave function on which it's acting. Okay, so in the next lecture, I'm gonna make a more detailed tour of all of this, both mathematically and physically. But for this, I'm going to stop here.